All right, so video on sampling distributions and the central limit theorem. And we have already discussed the normal distribution, the standard normal distribution for populations. All right, so we said when we have a population, we use the Greek letter mu for the mean, sigma for the standard deviation, and we said that the random variable x is distributed as a normal distribution with some mean and some standard deviation. Normal distribution is a bell curve. The mean is in the center. We've already gone over these things. The important thing to think about now is that these are individual values that we're talking about. This is a distribution of individual values. These x's along the horizontal axis in this distribution are individual values. When we ask a probability question about this distribution, we're asking a probability question about an individual value. What's the probability that an individual value in this distribution is larger than something, less than something, between two values? All right, so now the major leap that we're making here is now we're taking samples of size n from a population. All right, so we have a population, it's distributed in some way. It can be normally distributed, it might not be. We'll get to that. But we take samples from that population of size n. So we take one sample of size n from the population. We get a mean, a sample mean, one value. Okay, that gives us that's called a point estimate. That gives us a very vague value of the center of the population distribution. It's not going to be the actual center. Think about it, we take another sample, we're going to get a different number for a sample mean. We take another sample of the same size, n, from the population. We're going to get another value for the mean. So theoretically now think, we're going to take an infinite number of samples from a population of size n, and now we're going to get a distribution of those sample means. And so that's what a sampling distribution is. Taking samples of size n from a population and getting a distribution of those sample means. So we want to know how that is distributed, how that sampling distribution of the sample mean is distributed. Notice the difference here. X without a bar, that's an individual value. X with a bar, that's a sample mean. That's an average of n values from the population. That's going to be distributed normally. There's two cases here. And this is where the central limit theorem comes into play. If we're told that the population we're taking the samples from is normally distributed, then we know immediately we can go to this and say the sample means are distributed normally also. They have the same mean as the population. What changes is the standard deviation of that sampling distribution. And you can see how it changes. Instead of the population standard deviation, it's the population standard deviation divided by the square root of the sample size. And the sample size is always a positive number, so realize this number is always going to be less than the population standard deviation because means vary less than individual observations. You will sometimes see this term called the standard error of the mean. Don't let that confuse you. The standard error of the mean is the standard deviation of the sampling distribution of the sample mean. All right, good times. So when we take a sample, we know the sample means. If the population is normally distributed, we know the sample means are also normally distributed in this way. What the central limit theorem says is that no matter what the shape of the population distribution, so let's say we take samples from a uniform distribution or some other distribution that we haven't even talked about, exponential or hypergeometric, these things that we haven't even discussed. Doesn't matter what the population distribution, how it's shaped, if we take samples of size 30 or more, and that's kind of just an arbitrary number, we just use 30 kind of to be safe. So if sample sizes are 30 or more, doesn't matter what the population distribution shape is, the means are going to be normally distributed in this way. And once we establish that, then we can ask probability questions about the sample means in exactly the same way that we ask probability questions about the population distribution. And that's the major leap here. And now we're going to, for the rest of the class, we're going to concentrate on two sample statistics. The sample mean, we're going to be very interested in the sampling distribution of the sample mean. And in my next video, I'll start talking about sample proportions. Okay, so those are the two things we're going to be concerned with. Right now, we just want to understand what a sampling distribution is and what the central limit theorem tells us about that sampling distribution of the sample mean. So let's look at an example. Let's say, I'm just going to make up some numbers here. Let's say we have a population distribution that's normally distributed with a mean of 70 and a standard deviation of 12. Okay, so we're given this information that the population distribution is normally distributed, has a mean of 70 and a standard deviation of 12. So we are going to take samples from this population that we just defined, and we'll say we'll take samples of size 36. I'm using that because it's going to be a friendly number in our calculations. So even though we were told, we didn't need to be told that the population was normally distributed with this kind of sample size, it doesn't matter. But for sure, we can now use the techniques that we just talked about and say the sample means from this population of samples of size 36 are going to be distributed in this way, right? The sample mean is going to be distributed normally with the same mean as the population, but the standard deviation is going to be divided by the square root of the sample size. All right, so now you can see why I use 36. Square root of 36 is 6, so 12 over 6 is going to give us a nice even 2 as our sampling distribution's standard deviation. This is called the standard error of the mean, which we described over there. Standard deviation, sometimes called the standard error of the mean. So once we're up to here, and then 12 divided by 2 gives us the 2, now we're just answering probability questions about the sample mean of size 36 from the population distribution. So we can answer all the usual questions that we're used to, hopefully by now. What's the probability that the sample statistic is less than some number? We know how to deal with that. That's the easiest question, right? We just standardize because we know it's a normal distribution. So we can standardize this statistic to a z-value by subtracting the mean and dividing by the standard deviation. We do the same thing to the value, 73.5 minus the mean divided by the standard deviation. We get our z-value of 1.75. And just like we did previously, we go to our table and look up that number, 1.75. Now, again, realize that's the most straightforward question since it's less than. We know the table gives us probabilities less than the value that we look up. So all we have to do is look up 1.75 in our table. And we know how to do that, hopefully by now. Let's make this even bigger. Okay, so 1.75, here's the 1.7. We go over to the 0.5 column, 0.5. We go down to the 1.7 and over to the 5, and we see 9,599. 9,599 is our answer. Okay? So we put that here, that's our answer. That's the probability that when we take samples of size 36 from this population, the probability that that sample mean is going to be less than 73.5 is very close to 1, right? Almost 96%, 0.9599. And again, ask if that makes sense. Well, let's see. This is more than one standard deviation away from the mean. 3.5 divided by 2. We did say, oh, did I do that right? Did I find the right number? See, and I'm thinking that might be a little big. All right, so let me go back and double check. and make sure I got I think I said 1.5, right? It's 1.75. No, that was right. 1.75, 9599. So we were right. I was right. Seems a little high, but it's almost 2 standard deviations away. Remember the 68, 95, 99, 7 rule. If we go out plus and minus 2 standard deviations, that's 95% of the values approximately. So that would leave more than 97.5, which now it kind of makes sense when you think about it like that. So 96%, because again, 95, the middle 95, so that leaves only 2.5% above this number if it was 2 standard deviations, which it almost is. It's 1.5. And that's why it's less than 0.975. Okay, so 9599. And the other directions, what's the probability that X bar is greater than 69.3? So once again, we standardize, and I'm going to use the complementary method here for the greater than. Remember, you can use the idea of symmetry also. I'm going to use the complement. The probability of the X bar being greater than this number is 1 minus the probability that it's less than that number using the idea of complements. I standardized the 69.3 by subtracting the mean, dividing by the standard deviation, and you can check me on this. This is the Z value that you get. So when we look that up, negative 0.35, negative 0.3, here's the negative 0.3, this is the 0, the 1, the 2, the 3, the 4, the 5, 3632. So 1 minus 3632 is going to leave us with 6368. I believe, is that right? 632, I believe so. Okay. So again, just looking numbers up in the table, we standardize the 69.3 to get negative 0.35. We look up 0.35 in the table, we get this number. We subtract that from 1 to get our answer of 6368. And then the in-between question, which again, hopefully we're getting used to these questions by now. Any probability distribution involving the normal distribution, we can standardize in this fashion. I used the same numbers so that we wouldn't have to take up too much time. We already found the probability less than 1.75. That was here. Right, 9599. And we already found the probability Z is less than negative 0.35. That was 3632. And remember, this is how we find the probability between 2 numbers. We standardize first. We already standardized the 69.3 to the 0.35, and we standard 73.5 to 1.75. We take the probability less than the larger number, that's this, and we subtract the probability less than the smaller number, that's this. We look this number up in the table, we get this. We look this number up in the table, we get this. We do the subtraction, and we end up with 9599 minus 3632. So we end up with 5967 as our answer. All right, so good times. Sampling distribution. So the main leap again, we're taking samples of size n from a population. These are individual values. These are means of n values. What changes is the standard deviation of the normal distribution. The central limit theorem tells us the population distribution does not have to be normal as long as the sample size is greater than or equal to 30. And once we have that information, we take the population, we look at the distribution of the sample mean, and then we can ask probability questions about the sample mean, just like we asked probability questions about the individual observations. All right, see you next time.